you'll work on that. Homework should be pretty reasonable. So let's talk about rates of change. So this is kind of the beginnings of calculus, and it does incorporate limits. So we spent all this time on limits. We did kind of a lot of mechanical things with limits, like sine x over x. You know, when x is approaching 0, we saw that was 1. Or we saw for rational functions, like depending on the degree of both top and bottom, when x is approaching positive or negative infinity. Sometimes we saw horizontal asymptotes. We talked about x approaching infinity, and that gave rise to infinite discontinuities or vertical asymptotes. We did a lot of technical things. We're not going to kind of take that and apply it in a more practical sense, if that makes sense. Sorry for repeating myself, but so we're going to talk about rates of change and how things change as time passes. So here's kind of an interesting example. And I should change to my name or a different name, but Mrs. Blanford was the one who taught AP Calculus for the longest time. She retired 4 years ago, so don't worry about the teacher's name. I should have changed that. But this teacher persuades Mr. Dioli to get a Twitter account, or X, as it's called now. And his username is second most happiest place. Do you guys know why he calls it the second most happiest place? Go on. But even more, there's a deeper reason. Second S H B. It's a really good marketing for that, Mr. Dioli. Second most happiest place on earth, Sacred Heart Prep. It took me about 10 years to figure that out, so I'm not sure you guys knew that. But when he says second most happiest place, yes, he's referring to Disneyland, but it's also a play on words of Sacred Heart Prep. Anyway, in case you guys are curious. So anyway, let's say he gets 30 followers after 3 hours, 100 after 5 hours, okay? So all of a sudden, he has this account, people get excited, oh, well, I want to chat with Mr. Dioli, see what he says, you know? So he's getting more followers as time passes, right? So what we're going to do is we're going to talk about the change in the number of followers for the first 3 hours, the change in number of followers for the next 2 hours after that, from hours 3 to hours 5. So anyhow, how many followers did he gain for those first 3 hours? He gained 30 followers, right? How many followers did he gain from hours 3 to hour 5? 70, good, exactly, perfect. So the question is, during which of the two time periods is the number of followers growing faster? So what you could do is think of like a slope, right? And slope is a big deal here, guys. Slope is actually the whole essence of what we do for the rest of the semester. It comes down to slope, but you know, thinking through a calculus lens. So I drew a blue line and a green line. The blue line connects 0, 0 to 0 to 330. And the green line connects 330 to 5100. Which one thinks steeper? The second one, right? The green one. So I would say the second time period has a faster rate, right? And one way to see this is Mr. Dioli's accumulating followers in the first 2 hours at a rate of, well, that's going to be 30 over 3, or 10 followers per hour, right? That's his rate for the first 3 hours. And by the way, units are incredibly important. In the next 2 hours, what was his rate for the next 2 hours? 35, totally right. 35 followers per hour. Great. So what we usually say when we express these rates, we express them as an average rate of change. Let me get a highlighter, actually, it's probably a little better. An average rate of change. And I'm just going to repeat the numbers I just computed. 10, and 35. I'm not going to write the units because I'm just being a little lazy right now. An average rate of change is usually measured in time, like per hour, per minute, per some unit time. They don't have to be, though. And we'll talk about that in a little bit. You don't necessarily have to express a rate with time in the denominator. Yes, when we think of rate, you think of like maybe how much money you make per hour, right? Like an hourly rate, like what's the minimum wage, $20 per hour. Or driving, like I drove from here to San Jose at an average speed of 60 miles per hour. But average is exactly what it means. It's an average speed or rate or whatever for a certain time period. For example, let's say you drive from here to Los Angeles. You don't have to write this down, but let's say you drive from here to LA, I don't know, maybe 400 miles. And let's say it takes you like 8 hours. Okay, just say a lot of traffic, right? What was your average speed during that trip? 50 miles per hour. Now, did you go 50 miles per hour consistently the whole time? No. Maybe you went 100 miles per hour when there was an open highway. Maybe you slowed down to 10 miles per hour when there's a lot of traffic or an accident, right? So that's exactly what it means, an average, right, over a certain time period. That's what we're looking at right now. We are going to eventually whittle it down to an instantaneous rate of change or a rate of change at a particular moment. We're going to work our way towards that. And that's going to give rise to what we call the derivative or the slope of the tangent line. We'll get there in a while. Okay. So as I said earlier, rates don't always have to be per hour or per minute. It could also be in other ways. For example, the way Twitter or X works is that you tweet something and someone can retweet, right? So like, for example, you send a tweet, right? And then someone wants to share, oh, Jolie said this, so let me share this with all my other friends, right? So you're retweeting it, right? So let's say, for example, Miss Jolie gets 4,000 retweets from his first sport tweet. So he tweets, and all of a sudden, people are sharing his tweets, right? So what's the average rate change of his retweets? I know, try to say it really fast. 4,000 or 4 or 1,000 retweets per tweet. That makes sense. So you can think of it like this. Like right now, he doesn't send any. After 4 hours, 4,000. Does that make sense? So really, the average rate of change is thought of like this. F of B minus F of A over B minus A. So you think of it like slope. And actually, to be more specific, slope of a secant line. Do you guys know what a secant line is? From geometry honors, maybe? You guys remember? Okay, secant line is simply this. Let's say I got some funny curve. Say it's A. Say it's B. That's a secant line.
So just the regular line.
Passes to, yes, exactly. A line that passes through 2 points on a curve. That's a secant line. So we'll be using that term quite a bit. Tangent lines, I think you guys know, tangent means touches at one point, but secant line passes through 2 points. That's an average rate of change. Sorry, the slope of the secant line is the average rate of change. Okay, so I want to make sure we're comfortable with that terminology. Again, the slope of the secant line is the average rate of change, or vice versa. So let's look at these two examples here. Find the average rate change of ln x over the interval from 4 to 12. Okay, so simple. You're just going to do f of 12 minus f of 4. So it's natural log of 12 minus natural log of 4 over 8. You can leave your answer like that, by the way. On the AP exam, actually, that's what they're cool with that. If you did want to approximate it, but do need a graphing calculator, should be pretty easy. I get 0.137. And by the way, for rounding, get in a habit of rounding to 3 decimal places. That's what's done in the AP exam. Again, you guys are not doing AP calculus exam until 2025, but just get in the habit of doing that. You could round up or truncate or even get more, but at least 3 decimal places. Okay, for number 2, what am I going to do for number 2? How do I do that one, guys? Yep. Over 2 minus -2. Which should be 16 over 4. Or 4. So what does it remind you of? Again, slope. I kind of got ahead a little bit here. Slope of a secant line. Okay. Okay, cool. All right. So this is important. This is the kind of the aha moment that comes to calculus. So a tangent line is when a line touches a curve once. So this is a tangent line right here. That's a secant line. So this is probably from geometry. You guys remember that, right? Tangent lines, secant lines, right? Okay. So it just grazes it. Now, I'm going to actually put quotations here around once because I kind of didn't tell you the full truth. This could potentially happen, just so you know. So this right here, let's say I have a point right here. I have a line that just grazes it. So it touches it once, right? However, is it going to touch it again? It is. So in some ways, you have to be mindful that when I say once, it's not 100% accurate. But what it does mean is that it's a tangent grazes. And it may touch again later on. But this right here is called the instantaneous rate of change because you're trying to find the slope of this at a particular moment. We're going to talk about that in this example here. So this example or demonstration, let's talk about. So we have y equals x squared. Let me zoom out a tad. Okay, I think we're okay. All right. So you guys have y equals x squared, right? Easy peasy. And point P is at 1, 1. And you're trying to find the slope between P and Q. And Q is going to change a few times. Q is going to be 749 initially. And then what's happening is that Q is getting closer and closer to what? 1, exactly. So we're going to start noticing some sort of pattern here. So, and actually, in the interest of time, I'm just going to show you the filled out version of the notes. This is the beauty that having taught this class, I have all these filled out notes. Not my handwriting, by the way. It was the person who taught this class before I didn't co-taught it with me until she retired, Mrs. Blanford. I'm going to have you copy these down first. Let me zoom in just a bit more. Just in the interest of time, I'll just display this. So, you find the first slope. That's pretty easy, right? 49 minus 1 or 7 minus 1, that's 8. And then you find the next slope, it's 6, then it's 4, then 2.5, 2.3. By the way, so 1.5 divided is x squared, right? So we're looking at a parabola, a very simple parabola, y equals x squared. And then, of course, 1.3, 1.1, and 1.0. What do you notice is happening with the slope? I have to do each calculation. It's getting closer and closer to what number? It's getting closer and closer to 2, right? So if you look at that question down below the table, does the slope appear at a limiting value as Q approaches P? Yeah, probably 2. And so this is kind of that aha moment, is that we start seeing why we're looking at limits before we do derivatives. This right here is called a derivative, which I'm going to talk about in just a few minutes. But ultimately what's going to happen is that you have y equals x squared, right? We know this. Here's 1. Here's 1. Okay. And it looks like the slope of this tangent line is 2 at 1 comma 1 for y equals x squared. Does that make sense? So slope of the tangent line is 2 at 1 comma y equals x squared. That's what we're noticing. So let me go. Do you guys get a copy of the table? You good? We're cool? All right. No, yeah, you're still copying? Oh, right. Okay. At y equals x squared. So yeah, so does this appear to have a limiting value? Again, I said yes. Probably 2. The limiting value, if it exists, is called the slope of the curve, or the tangent to the curve, is the line through P with this slope. We also call this the derivative, which we'll talk more about on Friday. So the slope of the curve is what we're trying to find, or the tangent line, slope of the tangent line. So here's how we actually do it from an analytical viewpoint. It's a little bit funky at first. There is actually a much better way to do this, just so you know. But we're going to do it this way first. Let Q be the point 1 plus h, comma f of 1 plus h, where f of x is x squared. So really, it's going to be this then. 1 plus h comma 1 plus h squared. H can be either positive or negative, by the way. So in this case, here's P. That's at 1. This is at 1 plus h.
The 1 plus h is actually an x value, and h is the change between these two x values. In this case, is h positive or negative? This is right, obviously, right?
Sometimes we call this delta x. Kind of get used to that term, that symbol. In this case, our delta x is h.
Delta means change, right? We're going to change lots. We're going to use this simple lot, this blue triangle. Delta. Delta x is h. So the difference between these two x coordinates is h.
So let's find the slope. Let's do it. So let's find the slope of PQ first. So you're doing f of 1 plus h minus f of 1 over 1 plus h minus 1. So that's going to be 1 plus h squared minus 1 over h. So it's 1 plus 2h plus h squared minus 1 all over h. Clean it up, you should get this. Okay, does that make sense? Okay. Now, here's the deal. We want h to approach what number? If I want a tangent line,
If I want Q to get closer to P, right? I want Q to get closer to P. What's h approaching? Exactly. And this is the aha moment.
This is the aha moment. So the slope of the curve is the limit as h approaches 0 of 2 plus h. And what is that limit, guys? 2. So this right here is the slope of the curve, or the derivative. The derivative of y equals x squared, x equals 1 is 2. You've now done your first derivative. Maybe you've done one before, I don't know. But this is the whole concept of a derivative. So if you want the equation of the tangent line, well, that's easy. You guys are familiar with this form of a line? You guys remember what that's called? Point slope. By the way, point slope is a standard that we use in this class. You'll be using point slope pretty much all the time. Yes, you could rewrite it in point slope, sorry, in slope intercept form if you want, or standard form. But usually you want to start with point slope form, just because you just plug and you're done. You don't have to do much else with it. You can leave it in this form. So yeah. So this is point slope form, you know this. And my equation is going to be this. Y minus 1 equals 2x minus 1. If I go to Desmos, just kind of investigate this a bit further. Yeah, you see how that, let me clear the screen for a moment. You see how it just grazes it, right? So yeah, that's what's happening. Easy peasy. Okay. So this is what we call the slope of the curve. It's a limiting case. There's also the derivative as well. Now, as you can imagine, we did something pretty simple with y equals x squared. But what if we have like really complicated equations and you're plugging a plus h and a, and by the way, a is some x coordinate where you want to find the derivative or the point of tangency. So a is the x coordinate. So this is what we're trying to achieve, right? We're trying to find a tangent line here.
We're trying to get Q close to P so that they coincide, right? Like right now, if I draw P and Q, is that a tangent line? It's a secant one, right? But as I let Q get closer to P,
So as Q approaches P, what does that mean? H is approaching 0, right? That will be the tangent line. And that's the derivative. In order to compute that for more complex equations, using this technique of like f of a plus h minus f of a over h and taking the limit as h approaches 0, it's going to be incredibly hard to do. There are going to be better techniques. We're going to learn a whole bunch of efficient techniques over the next few weeks. We won't finish derivatives as a class or a differential calculus because there's not enough time, but you guys will do more derivatives in the fall when you do BC calculus. Anyhow, so that's what this represents: the tangent to the curve, the slope of the curve, the derivative. All these different terms you use all mean the same thing. Another thing we need to talk about too. Anyone taking physics right now? Okay, you guys know about normal forces? What's normal force?
It's just the force, like something. If it blocks.
It points up, right? So your motion is this way, but the force is pointing up. Like for example, I'm not going to tilt this, I'll spill my tea. But if I were to tilt, or actually, if I think about like, there's gravity weighing down my laptop on this table, right? There's also normal force that's pointing up. So normal basically means perpendicular. It's perpendicular to your surface. So the normal line, I know I geeked out with the physics there, but that's okay. And by the way, there's a lot of tie-in between physics and calculus. Huge tie. So for those sophomores who are doing AP physics next year, this is going to help you guys tremendously, right? Because you're now have a better understanding of it because you're doing some calculus, right? So the normal line is perpendicular to the tangent line. So if I have something like this here, again, a very funky curve, and let's say this is A. I got a tangent line. That's normal line. And by the way, how are the slopes related for perpendicular lines? They're reciprocals, exactly, right. So if the green line, I'll call it MT for the tangent line. Let's say that has a slope of 2. Then the blue line, for the normal is -1/2. And it makes sense, right? Okay. Okay, example 4. We're going to work this out. Example 5, we're going to work that out. Example 6, we're going to work that out. We should be done in the next 15 minutes, I'd say, and you guys can get head start on homework. So here's what we're going to do. Find the slope of the curve at x equals 2. Great. Let's do it. So my slope is going to be the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. Does that make sense so far? We're good? Yeah. Okay. Then you just got to do a bunch of algebra at this point. Now, first off, you have to keep writing the limit notation, so you can't get lazy about it. And as I told you, this is not very fun because you have to expand this. Fortunately, I give you the expansion up here. So you have to FOIL that 3 times. We're not going to always keep doing it this way, just so you know. We will have better ways of doing this. I'll show you that. Probably not until May sometime is my guess, is when we'll do that. So here we go. We got 8 plus 12h plus 6h squared plus h cubed. How do you think I'm doing that, guys? Yeah, exactly. My a is 2, and my b is h. So if I do a cubed, it's 8. If I do 3a squared, b, that's going to be 12h, and the other one's going to be 6h squared, and then plus h cubed, minus 4. Wait, did I do that right? Oh, sorry. Yeah, sorry. There's still that part too. Geez, I got ahead of myself. Thank you. Okay, there we go. Cool. Question? -4 minus 2h. Oh, from this part. Yeah, let me do this. Because this is where it gets really confusing, and this is the beauty about Zoom, is I can actually color code really easily. Yeah, I hope that makes sense now. Does it make sense, guys? We're cool with that? You guys see the color coding? Okay. Let me erase some stuff here. Eight. Okay, what cancels? Yeah, 8. And by the way, that should happen. The top one have a bunch of h's. If you don't, you got a problem. Because right now, if I put in 0 up here, I have 0 to 0, right? That's gonna be a problem. You want the constants to cancel. Because once the constants cancel, and let me combine like terms. I've got myself 10 h plus 6h squared plus h cubed what can I factor out from the top, guys? Yeah, totally. Mhm. See those cancel? Now can I plug in 0 for h? And what happens if you do? You get what? There you go. So slope is 10. I'll go to Desmos in just a sec. So does that make sense what I just did? Okay. Do need a little space. I'm going to delete some other things here. Part B. Y. If I put in 2, you can leave your answer like that, by the way. And then for C, so I don't care if you write it in slope intercept form, but if you do, you get it wrong, you lose points. So my suggestion, keep the answer in point slope form. It's not necessary to change it to the college board doesn't care. So just leave it in point slope form, okay? Does that make sense? All right. And then let's just, just check, make sure we did this right. Just go to Desmos. X cubed minus 2x, is that correct? Y minus 4, 10. Yeah, see, that totally makes sense, right? Yeah, that makes sense. So yeah, we're cool. Okay, we're good? All's good? Okay. All right. We'll see another one here. So let me tee this up for you guys and then have you guys try it on your own. So we'll do a limit as h approaches 0. So m will equal all that junk. Need a little more space. 1 over 5 plus h minus 3 minus 1 over 5 minus 3 all over h. Or it'll be 1 over 2 plus h minus 1/2 Okay, that's what we got to work out.
Point 0 right now, you have a problem. You have 0, 0. That's a problem, right? You point 0 right now. Anyone have an idea what we should do next? Algebraically, what should we do next? Go ahead, Kate. Find the common denominator, exactly. What's the common denominator between these two?
2 times 2 plus 8.
Exactly right. So I'll let you guys take it away. Clean it up.
So it's a lot of algebra. That's really, I'm confident you guys can do the algebra because you guys got to this point in this class or in your math career. But you can see why some people struggle with calculus because they never refine their algebra skills. It's sad that sometimes we pass people on to calculus and they have crappy algebra skills and then they wonder why they just can't do it because, dude, you never conquered algebra. There's a lot of that. The calculus part's not hard. It's the algebra, actually, I'd argue is the hardest part. Calculus part's easy. The setup, that's all the calculus part. The execution is the algebra. You got to execute that perfectly. So I'll pause or I'll freeze and let you guys work it out, and then we'll compare in a couple minutes. So.
Oh, that's. I think you're right.
You guys should get -1/4. Yes. And by the way, that should make sense. So why do we spend all these years, in algebra 2 trig honors and beginning of this class, and even middle school when you're doing algebra and you're learning about curves? Why did we do that to you guys? Because you guys are wondering, like, what the heck? Like, when am I gonna graph a rational function, understand the asymptotes and all that stuff? It's for these moments. So if you guys remember, this is a rational function, right? And the curve generally looks like this. And this is a decreasing function because y keeps decreasing as x increases, right? As x gets bigger, y is going down in value. Well, look at 5. Look at that slope. What would you say the slope? Would that slope look negative to you? Does it look like it's probably -1/4? Yeah. In order to understand this, you got to be able to visualize graph. You got to make that connection. So you got to be able to visualize a graph in order to understand the calculus that goes into it, right? So now we're applying a calculus principle. This is a derivative, this slope of a tangent, or we call it instantaneous rate of change. Yeah, that makes sense because I see how the curve looks. I see at x equals 5. Yeah, that should have a negative slope. This is why we spent all these years forcing you guys to do these types of graphs. So when you apply calculus principles, it makes more sense. Now, are things modeled in the real world using rational functions? Sometimes they are, sometimes they're not. But other things we'll model, like exponential functions, are usually more practical in the real world stuff, or polynomial models sometimes. And we have to apply calculus principles to those. But that's what we spent all these years teaching you all this math. Like, it's not just for the fun of it, but it's all actually be practical when we get to calculus. Okay, I'll get off my soapbox. Let's do one more example, and then we're done. And as true to my word, we'll be done by 9:15, and you guys can start homework. You have about 25 minutes. I think you can get the homework done. This one here. At what points does the tangent to the curve of this have a slope equal to? Well, let's find the slope of this quickly. So limit as h approaches 0. I know it's kind of a pain. You have to keep doing this. Okay. Does it make sense what I just did? Does it make sense? We're okay with that? I'll slow down. I'll slow down. So remember, you have f of x plus h, or actually, I should have done a instead of x. That's okay. I replaced x with x plus h, and that's what you guys noticed that. We were using a plus h, or like 1 plus h, 2 plus h, like whatever the x coordinate of the point of tangency. Remember, we're putting that for x. I'm just more generally sorry. I should have. Sorry if I'm confusing you guys. I'm doing this slope in terms of x. Instead of at a particular point on a curve, like we did with 1, 1 x squared, or we did an x minus 2x at x equals 2, so I plug in 2, right? Or at x minus 3, I plug in 5. Sorry, I'm doing this in terms of x. I'm doing a general slope of the curve, or if that makes sense, or the general derivative. So my apologies, I should have mentioned I was doing that. So what I'm doing here is f of x plus h minus f of x over h. Okay, what cancels out? Yeah, anything that doesn't have h is out. So now I can factor on h. Oh, hold on a sec. There we go. Forgot about the negative 3h as well. What happens to h's? Cancel. If I plug in 0 for h, what do you get? So 2x minus 3 is a derivative of x squared minus 3x plus 1. Now, for part A and part B, you're asked, at what points does the tangent curve have a slope of 4 or 0? So you set 4 equal to 2x minus 3. If you do that, what does x equal, guys? 7 halves. So if I plug in 7 halves back into the original equation, (3.5) squared minus 3 times 3.5 plus 1, I should get 2.75. So the answer for part A and for part B, it should be 1.5 comma negative 1.25. Which, by the way, what do you think that represents? Part B. You have a parabola. You have a slope of 0. Slope of 0 is a horizontal line. Good. Thank you. Vertex. Yes, that's a vertex. You can find the vertex really easy using calculus. I mean, this technique is a little messy, but trust me, there'll be a faster technique that I'll teach you guys. Actually, I might tell you that fast technique in just a sec because I feel like you're going to find out anyway. But let me graph this in Desmos really quickly. So x squared minus 3x plus 1, x squared minus 3x plus 1. If I locate 3.5, let me clear my screen. Yeah, you see 3.5? There you go. 2.75. So that'll have a slope of 4 if you were to graph that. If you graph that tangent, or here, there you go. Found my vertex. So you can find highs, and so the one advantage to derivatives is that ultimately we want to find highs and lows. There's a great business application. Actually, we won't do it this semester. We will do it shortly. We start BC in the fall. Something called optimization, where like they might give you like a cost function or a profit function. Say, I want to maximize my profit. I want to minimize my cost. Because in business you want to make money, right, and not spend money. And so you might be given like these formulas, like, okay, here's a model we have for our profit, and maybe it's in terms of X, like X is how many items you sell. So how many items do I have to sell to maximize my profit? So you want to find a peak. How do you find the peaks? Like when you were graphing like polynomial functions, you weren't quite sure how to find the highs and lows exactly. Now you can, because at highs and lows, the tangent line is going to be 0, right? That's what we're seeing here. So this is the beauty about calculus. I get really excited about this because I think this is the coolest class math. But anyway, that's my humble opinion. Really quickly, we know the answer is 2x minus 3, right? Anyone see mechanically what you can do to x squared and negative 3x? Yeah, there's something called the power rule, which I'm really kind of being incredibly premature telling this to you guys right now. But if you want the derivative of it, you move the exponent to the front and you drop the exponent by 1. And if you have a constant, you assume it's multiplied to x to the 0. But that becomes 0. That becomes negative 3, and that becomes 2x. It's called the power rule. So there's a shortcut you can do. You can take the exponent, move it to the front, drop the exponent by 1, but only works for polynomial terms, this little technique here. If we have like sine, tangent, e to the x, log, root x. Well, root x actually could work too. Anyway, I'm getting a little ahead of myself here. For now, you have to do the whole a plus h thing. Sorry, you have to do it the long way because you have to understand the limit behavior before you move further into other techniques. But I know you guys can look up the shortcut rules, or someone can tell you that. Like, dude, just use a shortcut rule. So, anyway, I'm all done.